Hello everybody, hope all of you are well, and today I will continue your carbohydrate chemistry chapter. Okay, so last day we have discussed about alpha D and beta D glucose. Okay, they are in equilibrium, and if you take the freshly prepared aqueous solution of alpha D glucose has a specific rotation plus 112 degree. When the solution is allowed to stand, the specific rotation decreases gradually to attain a constant value, that will be plus 52.5 degree. Okay, and similarly if you take the aqueous solution of beta D glucose has a specific rotation plus 19.5 degree, and which on standing, if you keep the solution for some more than 1 hour, then what will happen? The specific rotation value will increase from plus 19.5 to 52.5 degree. So this spontaneous change in specific rotation of an optically active compound in aqueous solution with time to an equilibrium value is known as Noether rotation. So this Noether rotation is very important for glucose, Noether rotation. Okay, actually alpha and beta form are in equilibrium. Okay, and whenever any solution if you take, finally you will get the specific rotation of the resultant solution as plus 52.5 degree. Okay, this is very important. Next one we will discuss the structure of fructose. Okay, in fructose there is one ketone group. So here we are writing that CH2OH, C double bond O. Then hydrogen will be this side, and there will be OH. Then OH will be this side. Then there will be H. Then again there will be OH and H. 1, 2, 3, 4, 5, and finally there will be CH2OH. So this is the structure of the fructose. Now this fructose is also, like glucose, is forming ring. Okay, here if we give number, then you can understand 1, 2, 3, 4, 5, 6. So when the ring is formed between these 2 and 5, these 2 and 5, okay, then we are getting the two form, that is alpha D fructose and beta D fructose. So here we are writing this one at C, OH will be that side and CH2 will be this side. And this is forming the ring CH, OH, COH, H, and CH, O, and here it is forming a ring. Okay, and this is called that alpha D fructose. Alpha D fructose. If you want to write the beta form, when this OH will come this side and CH2 will go that side, then it is called the beta D fructose. So again I am writing this form also, that here this side CH2OH and this side is OH and CHOH, COHH, CHO, CH2H. This one is the beta D fructose. Now here the total number of atom in the ring is 1, 2, 3, 4, 5. So these 5-membered rings are, if we draw the structure in Howard projection, that is pyranose type. Okay, so Furanose type. So if we draw the structure, then you can easily understand. So here I am drawing the Howard projection formula. Okay, here we are drawing this alpha D from, okay, this alpha D fructose. Now here the CH2 which group will be at the top and OH will be at the bottom, then OH here, this one will be the H, here H, this one will be the OH, in the cyclic structure, okay, and here CH2 which will be the top and this will be the H. Okay, so this is the alpha form, and whenever we want to write the beta form, this OH will go to the above and CH2 will go to the below. Okay, so that will be the beta form. And if there is formation of ring between these 2 and 6, then we will get the pyranose type structure. If ring is forming between 2 and 6, then what I will get here? So first I am writing this OH this side and CH2H this side. Then CHOH, then COH, H, then COH, H, then CH, H, O. So it is forming 1, 2, 3, 4, 5, 6 member ring. Okay, and this form as OH in the right side is called alpha D fructose. And in the same way there will be beta form also. Here also we can draw the structure Howard projection formula. This will be like this, and we are writing this alpha. So here CH2 will be at the top position. So this one is alpha D. Here it will be the OH, and here it is the OH and H, and next H is here, OH is here, is H, OH, and this one will be the CH2H will be at the here so CH2H already given, this is H and H. Okay, so this is the alpha D from, okay, and when we are writing beta D, so CH2H will be the bottom and OH will be at the top. So you can understand the cyclic structure of the fructose. Next we will discuss that test for glucose and fructose. You can do bromine water test. Glucose on reaction with bromine water readily decolorizes and it will oxidize to gluconic acid. Okay, already we have discussed this reaction, that CHO, CHOH whole 4 and CH2OH. Here we are giving bromine water, that is oxidizing, mild oxidizing agent. So this aldehyde group will convert into acid group. And this compound is called gluconic acid. And bromine water color will be decolorized. Okay. And if you take the fructose does not give this taste. So if you add bromine water to this fructose, there will be no color change. That is, the reddish brown color solution will not change. Okay, it will not be colorless. So from there you can easily identify which one is the glucose and which one is the fructose. Another test you can do, that is the perfural test. Fructose on treatment with alcoholic alpha-naphthol and concentrated HCl gives violet coloration, and glucose will not respond to this test. Next we will discuss another disaccharide is there in our syllabus, that is the sucrose. Sucrose is a disaccharide compound. Okay, it is a common disaccharide and it is sweet in taste, very sweet. Okay, and actually if we draw the structure, then you will get that alpha D glucopyranose and beta D glucopyranose will be attached with the alpha beta glycosidic linkage. Okay, if we draw the structure, then you can easily understand this structure. So first I am drawing this Howard projection formula so that you can easily understand. So first we will write that alpha D glucopyranose. Okay, so this one will be H, OH, this one will be H, OH. Okay, next will be the OH here, H here, then H here, OH here, and finally this one will be the CH2OH and H. So this form is the alpha D glucopyranose. Alpha D glucopyranose. And it will be attached with beta D fructofuranose. Just now we have drawn the structure, that is OH, CH2OH, then there will be OHH and HOH, and this side will be HCH2OH. And here this OH will take this hydrogen and there will be formation of glycosidic linkage. Now I am drawing. So this oxygen is attached with this CH2OH. Okay. Now you see here that here it will be the OH and here is oxygen and here CH2OH, H, HOH, OHH, HOH, and this one is OHH, HOH and HCH2OH. Okay, so here whatever you are getting this linkage, this is called the glycosidic linkage. Okay, alpha beta glycosidic linkage, and this is the structure of sucrose. Okay, now if you check the specific rotation, okay, sucrose is dextrorated, it will show plus 66.5 degree rotation. Okay, but if you hydrolyzed, then you will get the equimolecular mixture of glucose and fructose, and glucose rotation you know that is plus 52.5 degree, and fructose you know that is minus 92.4 degree. So since the specific rotation of fructose is more than that of the glucose, the resultant solution becomes the levorotatory. Okay, and this phenomenon is known as the inversion of cane sugar. That is also very important, that in case of sucrose, that is what is the questions, many times it will come as questions that what is inversion of cane sugar. Next we will discuss maltose. Maltose is also a reducing sugar which on hydrolysis gives two molecules of D-glucose. In maltose, the two glucose molecules are linked through the alpha glycosidic linkage which is formed between the C1 of one molecule and C4 of the other molecule. Next we will discuss the lactose. Lactose, this is also a reducing sugar which on hydrolysis will give the beta D glucose and beta D galactose. So in lactose, beta D glucose and beta D galactose are linked through beta glycosidic linkage which is formed by the C1 of the galactose and C4 of the glucose. Next we will discuss the polysaccharides. Now what are polysaccharides? The carbohydrates which upon hydrolysis gives a large number of monosaccharides units. Okay, they are called polysaccharides. For example, we can tell that starch, we can tell about the cellulose. These are called the polysaccharides. Hope you can understand. Next, we will discuss this starch and cellulose. Okay, so starch formula all of you know. Starch is a polymer of glucose. C6H10O5 N. So this is the formula of the starch. Starch is a polymer of alpha D glucose and its main source are rice, potato. These things contain starch. It also contains two parts. One is called amylase, another is called amylopectin. So amylase, another is amylopectin. The percentage of amylase will be around 20%, but amylopectin is 80 to 85%. Okay, so amylase is a water soluble component, okay, of the starch, and it is linear polymer of alpha D glucose which are connected through alpha glycosidic linkage, and the linkage is in between the C1 of the glucose unit and C4 of the other glucose unit. And in case of amylopectin, it is a water insoluble component of starch, and it contains 80% of the starch, 80 to 85%, and it is composed of 25 to 30 alpha D glucose units which are connected through alpha glycosidic linkage. Next we will discuss cellulose. Cellulose. Now cellulose formula also same, C6H10O5 N. Okay, C6H10O5 N. It is the major structural polysaccharide in plants, in higher plants. Okay, the cell walls of plants, okay, and vegetable tissues are made up of cellulose. It is a linear polymer of beta D glucose which are connected through beta glycosidic linkage. Okay, next we will discuss the function of carbohydrate. All of you know these carbohydrates are the major source of energy. Whatever food we are taking every day, maximum is carbohydrate, and we are getting energy from this carbohydrate. This carbohydrate that will make the cell wall of the plant or wood, okay, and it acts as a food preserve, okay, food reserve in plants. In plants they are reserving food as starch, and in animals they are preserving food as glycogen. So in this way we have completed the discussion of the carbohydrate, what is in your syllabus. So next day we will start protein. So today up to this, thank you.